Hello, my name is Oleg. Our team project is real-time video decomposition via incremental subspace learning. In simpler words, it's just real-time video background removal. And today I'll explain it in linear algebra terms. So first, I'll define our input. We have video, which is a sequence of frames. I'll denote a frame at time t as ft. It's a tensor with this shape, with height, width, and color channels. But we also need to preprocess this tensor. So what we can do is we can resize it to, let's say, 640 by 480 pixels. We can also optionally reduce our color channels to 1 so that we get a grayscale image. Then we need to convert each value to float, so we divide by 255 to get values in the interval 0 to 1. And then we can flatten our vector and get x, which is just a vector with all this preprocessing of ft, and which is now in this space where n is just multiplication of height, width, and number of color channels. Then we can actually define our data matrix. Our data matrix is just columns of our preprocessed vectors, which looks like this. Next, we need to compute empirical mean with this formula. After we did this, we can compute our center data. We need to do this as our algorithm works with center data. And next, we need to apply some sort of algorithm. We can use PCA, principal component analysis, for our video analysis, and for that we need to compute singular value decomposition with this formula. To get our U matrix, it's our background basis. What we do is we get only k leading columns, but computing a full SVD is expensive for streaming, because we need to do our project in real time, and therefore we only maintain some sort of k basis, and that's why I'll denote it as YT, which is a matrix of bases with only k elements, so its rank is k. And next, we can I can actually show you how we define our xt. It's we can define this as ls plus lt plus st, where lt is our vector with background, and s is our sparse foreground. And since we already have a basis matrix with our foreground, we can represent this lt as this matrix with some constant that will represent this vector and our foreground. And next, I'll show our linear transformation. So we have uh, a matrix that I'll denote like this. This is our transformation matrix. We use this to get our projection. This is our background projection, which we compute by doing linear transformation. And now to get our foreground, we need to compute the residual. So in the end, we get this formula. Then to update this basis of rank k incrementally, we use not just PCA but incremental PCA. And to do this, we compute first of all our constant. T plus 1 is our new frame, because as first we form our data with let's say 100 elements, and then we can just update it by and compute our background estimation with each new arriving frame, compute a residual for it. And then what we get is, if norm of our residual is small, we can actually not change our basis, but just represent it with some coordinates in that basis. And in that case, we just don't do any more computation. But if it's significant, then we need to form a matrix k plus, with sizes k plus 1 by k plus 1. I'll do this here. This new matrix will look like this. And now what we need to do is compute SVD for this smaller matrix and update our UT with new basis vectors. So we still truncate it to k elements, so that each time we compute SVD of only k plus 1 dimensional SVD and not increase it our computation time. After that, we can proceed with getting our image. So for that, we have some projection which we computed, and with this we can reshape it back to the tensor like that, in this form, and then we can compute mask of our residual for each pixel, which will look like this. We can define this threshold by doing some practical testing. This threshold basically separates some background noise and actually moving objects which we want to save. So that's it for our project. As a summary, I can go through the pipeline again. We have some data. We then move to vectors and do some preprocessing. Then we do our low rank model which saves only first k elements. Then we do our background projection using some sort of linear transformation. And then we incrementally update this U using only small computation of SVDs. So we do incremental PSA rather than just traditional PSA, and we don't compute like big SVD every time. Thank you, that's it.